We were working through this particle motion problem. So in order to determine if the particle is at rest, we first have to get to the velocity function. We're able to do that from position, going through calculus, power rule, from position to velocity, the same thing as you would do from f of x to f prime. And then once you get to your derivative, then your derivative represents your rate of change of position, which in this case we call it the velocity function. After we got to the velocity function, we factored set equal to 0. We got 2 and 5. And we spent the time to create the velocity sign line. We get a lot of information from the sign line. So we inserted our critical value, our velocity zeros onto our slope, our velocity sign line. So 2 and 5. And we know that our 3 subintervals will basically all be consistent directions of motion. So we knew that once we found all the places where the object is motionless, then the 3 remaining subdivisions are going to be all the same direction within each subinterval. So we can use any value to test. So I test 0 here into the velocity function. I got positive, which means moving right. It stops, moves left, stops, and moves to the right. Okay, so we did C and D, which was just using the velocity and acceleration function. Now, I want to review E and talk about F. So we didn't quite get to F last time, so I want to finish that. So we want to make sure that we understand the distinction between displacement and total distance. So displacement is just where you are versus where you started. Okay, we don't care about if this object, this particle has changed direction and moved forward and moved backwards. We just want to know what's the forward progress that is made from the starting point to the ending point, and starting time to the ending time. So all you do is you find the final position minus the initial position, and that's it. You don't touch the velocity function. That's all you need. Final minus initial. If you get a positive, that means you made forward progress. If you get a negative, that means you made negative progress. And we don't adjust anything. Whatever number we get, that's our displacement. Now, total distance is a little bit more involved, but you can start with the same information as displacement. Okay. Total distance, however, we have to keep track of the fact that if this object moves right and then moves left, we got to keep track of everything as positive, positive progress. Okay. So, what information do we need? Well, we definitely need to know the starting position and ending position. So I'll put x of 1 and x of 3. Okay. X of 1 just means I want to find the location of this object. Where is this object on the x-axis at 1 second? And 44, same as information that we gathered from part E, and it ends at 48. Okay. However, this calculation is different from displacement if this object is changing direction somewhere in that time interval. So does this object change direction somewhere between 1 and 3? What does the velocity sign line tell us? It does change direction, right? It's moving to the right, and then at 2 seconds is going to stop. It's going to move to the left. So that's going to impact our calculation because there is a change in direction between 1 and 3. Now, if there was no change in direction, then your total distance and displacement is going to be the same. Okay? He starts at 44, he ends at 48. He's going to cover 4 units, and that's the end of the problem. But there is actually a change in direction. So we have to keep track of where does he stop, and we got to be able to mark that location. So we need to find x of 2. So x of 2, all we're doing is entering 2 into the position function to figure out where is this object located 2 seconds into this journey. So if I plug 2 in for t, I'll do the calculation here. It's going to end up giving us 55. So we have to understand how to use these numbers to arrive at the total distance. Okay. So you don't do this every time, but I think for now, just to kind of make sure that you understand where these numbers and how to work with these numbers. Right now, you can just put these numbers onto your number line. Okay, so let's just, doesn't have to be accurate, but you can put 44 here, you can put 55 here, and then 48 somewhere in between. So I want you to think of this in terms of you are on the number line, and then each step you can make a progress of 1 unit. So imagine you are starting at 44, and you're making your way out to 55. Okay. How many steps would you take to get from 44 to 55?
11.
11, because you did 55 minus 44. So it would have taken you 11 steps. But you're working backwards here. So from here, you're walking backwards from 55 to 48. So how many additional steps would you take? 7. So notice that everything you're giving me are positive numbers. And that's how you're going to approach distance as well. Just think, I'm going forwards and backwards, but I'm just keeping count of the number of steps I'm taking, right? I took 11 steps because 55 minus 44 is 11 steps. I took 7 steps, 55 minus 48 is 7 steps. It's quote unquote negative, but I'm treating every step as a positive number. So therefore, how many total steps are you going to take? 18. That's total distance. Now, sometimes students look at this and feel like, oh, I'm just going to find every location between 1 and my ending value, and that way I can just, figure out that distance. But we don't have to worry about anything in between unless there is a change in sign. Okay, you could test every number in between, but then you're doing a lot of work. Imagine if you're going from 1 to 50, and there's only change in direction at 22 seconds. You don't want to find every single location. You just want to figure out if there's a change in direction. If there is, find the location and then just pretend like you're walking along that number line and you're just counting your steps. And however steps it takes to get from one point to the next and back to that to another point, then that's your distance. Okay, so we want to make sure that we know how to arrive at these numbers and what numbers to use, and that how we're calculating our numbers, right? There's no negatives involved here. And you're subtracting to find that distance that you covered, but after you get to those distances, there's no negatives here. You're just adding your results. Okay.
Get 55 for x of 2.
Right, how to get 55. So 55 means where is this object located 2 seconds in? So you would enter 2 in for all the t's for the position function. So it'd be 2 times 2q minus 21 times 2 squared plus 6 times 2 plus 3. And then you would end up with 55.
Okay.
But I'm skipping all that calculation to kind of speed us along. Now on the quiz, it'll be easier. If I'm asking you to enter into a function, it'll be easier to calculate because this is a little bit much to do by hand. Okay. But the important thing is the process. I want to make sure that we understand the process and we understand how these numbers are found. Okay, so 18 feet. Okay, number 8 is also good, but I think I want to save that for when we review for our quiz. So I want to start on the next section of today's topic, which is product and quotient rule. So if you can turn to page 23. Yeah, 23. Okay, so product rule is a formula used to find the derivatives of products of 2 or more functions. So I said before that if we want to do power rule, that we have to make sure we resolve all the parentheses, right? And if I can't resolve all the parentheses, then I can't do power rule. Here, we're basically having a way to work around these parentheses. So if I have parentheses, I can go through and find derivative, but I have to go through this thing called product rule. Okay, so product rule is, let me just go through example 1 here. Imagine I had these two expressions, right? 3x minus 2x squared and 5 plus 4x. I can find the derivative of this graph of this function without having to expand everything out because I'm going through product rule. So product rule, we have to assign one expression as f, and we can assign the next expression as g. Okay. It doesn't matter which one is which. I just typically, whatever comes first, I'm going to name it f. Whatever comes second, I'm going to name it g. So if I want to find the derivative of the product of f and g, I'm basically letting the two functions take turns being the derivative and the other being the original function. So it's f prime times g of x plus f times g prime. And I'm sorry, I left off that prime there. So we can put that prime in place there. F prime of g plus f of x times g prime. So there should be a prime there. There should be an apostrophe there. So let's practice this rule for this particular problem. Y is equal to 3x minus 2x squared times 5 plus 4x. What is the derivative? What is the slope formula for whatever this graph looks like? It says find dy dx. Dy dx is just another notation that represents the derivative. So this just means find the first derivative. So I'll say dy dx equals. And I'm just going to label exactly what I'm looking for, okay? So I'm first looking for f prime. Then I'm going to pair it with a g plus back to f, and then multiply by g prime. Okay, so f prime is the derivative of this 3x minus 2x squared, which is what? 3 minus 4x. Okay, so that will go in that first slot. Multiply by the g function. The g function is just the original second term, no changes. Plus, back to f. So f is the first term, no changes there either. Multiply by g prime. So g prime is the derivative of my g of x function. So 5 goes to what? 0. 4x turns into 4. So only a 4 there. Now there's my derivative. There's my slope formula. So if I'm looking for a steepness of any point on this graph, I'll just insert into this, and whatever number I get, that's going to correspond to how steep my original function is. I could clean this up. I could FOIL all this out and merge and combine my terms. But right now, I just want us to practice this process product rule. Okay, any questions so far? Okay, so right now, product rule is going to feel like it's not completely necessary because we can just FOIL all that out and just rely on power rule. But product rule is going to be especially useful when these problems become a little bit more complicated and we're unable to rely on power rule, and product rule is going to come in really handy. Okay. Okay. I'll talk about some pitfalls with this process in a second when we get to the next page, but let's talk about quotient rule. So quotient rule is where I'm trying to find the derivative of a graph of a function that has a numerator and denominator portion to it. So quotient rule is formula for finding derivative of functions that is the quotient of two other functions. So let's say there's a numerator and denominator portion. I'm going to go through quotient rule. So here's quotient rule. Numerator is f, denominator is g, and it's going to look a lot like product rule. Okay, instead of f prime g plus fg prime, it's going to be f prime g minus fg prime. But then we got to, this additional part that a lot of students forget is there's also a denominator portion for your derivative. It's the denominator squared, this g of x squared. Okay, so let's do example 2 and see if we can see if this formula makes sense. So it says find y prime. That's just y prime, dy dx. They all mean the same thing. They just means find the first derivative. So y prime equals. So the top I'm going to call f. The bottom portion I'm going to call g. Okay, so let's just step through this piece by piece here. F prime is 3 minus 4x. All right, we're gathering a lot of information the same way that we did with product rule, right? Okay, g function.
5 plus 4x.
Good. The difference here is that there's a minus sign. Instead of plus, it's minus. Okay, back to f. And I made these the same expressions, so we're getting a lot of the same things here. G prime is just 4. But what a lot of students forget about quotient rule is that we got to also have that denominator component. I need to have a 5 plus 4x quantity squared. So right now we are not reducing, but if we were to reduce, we would clean up all the numerator. Now, I want to make sure that we understand this is a way that we cannot reduce, okay? We cannot take out one of the 5 plus 4x's as it stands. Why is that? Say it again? Why? Yeah, it's anytime something is attached to subtraction or addition, we're not able to cancel out. Now, if this is a 3 minus 4x, it will still be the same. This 3 minus 4x, nothing can cancel out, okay? Because technically this is everything's attached to that minus sign. If I can somehow factor a common factor from both these terms, then I can maybe reduce between numerator and denominator. But that's another danger of quotient rule is sometimes students reduce a little too soon and cancel out when the ability is not there, because it looks like you can. So yeah, careful with quotient rule and careful with when you reduce, because it's easy to get thrown off and be tempted into canceling things out that are not able to be canceled out. So again, it looks messy, but a derivative just does the job of telling us the slope. So whatever this graph looks like, I can identify any point and use this derivative to tell me the steepness of this point, of any point on this original graph. Right, the derivative is always just going to do the job of describing the slope of your starting function. Okay. All right, so let me see. Yeah, and I want to now point out some common mistakes. So we have plenty of space here. You can just create, so common pitfalls, common mistakes that I see. Okay, so one thing that's common is not recognizing the need for product or quotient rule and instead relying on power rule. So whenever you see a problem, you have to be able to recognize, oh, I need product rule here, or oh, I need quotient rule here. So here's one I want to point out. So if I want to find the derivative of this function, there's two ways I can go about doing it. I can distribute the root x through, combine distribute the root x through, get rid of all the parentheses, and then I can do power rule, right? Or I can do product rule, thinking of the root x as f, thinking of the 3x plus 2x squared as g, f prime g plus f g prime, right? Those are both valid ways of finding the derivative. However, we can't do this. We cannot treat these separately and find the derivative of each and then just tack on the multiplication in between. Root x, sometimes students would say, oh, that's just x to the 1/2. I'll make it 1/2 x to the negative 1/2 times, okay, and this is 3 plus 4x squared, so that's just 3 plus 4x. Okay, we can't do that. We can do that if there was a plus or minus between, because then they're independent. But we have to treat a multiplication as connected in ways that prevents us from being able to do things as easily as this, right? It feels easy. This feels like the right thing to do. Why can't I just find the derivative of these separately and then attach a multiplication in between? And the reason why is because they're connected in a way that is more than just the plus or minus. So we have to either go through product rule, or we have to go through the common, or we have to go through the appropriate steps of expanding out and then relying on power rule. So we cannot do this. Okay. The temptation there is, it is high to want to treat them like separate things, even though there's multiplication in between. Okay, the second mistake that I see is trying to take a shortcut from quotient rule. Sometimes there are ways, but this is not one way that we can do it. Sometimes I see students do this where they see, okay, well, that's power rule here, that's power rule there. So I'll just take the derivative of them separately, and that's a much faster way of getting to my derivative. Okay, again, that doesn't quite work that way. So I mean, if we could find a way to bring that denominator up, we could go through product rule, but that's something else that we haven't learned quite yet till tomorrow. So we really have to rely on quotient rule here. We cannot do this. Okay, even though this feels easier, it's not going to lead us to the right derivative. All right, so I just want to point those things out. Let's go to the next page, page 24. Now, typically, we're not going to have to do a whole lot of derivatives past the second derivative. But I do want to show you some important features about polynomials in general, and what happens if we were to continue to find the derivative over and over again. So let's just see what happens after, as we find each derivative, and see what happens to each of the terms and see if we can identify some patterns. Okay, so let's just go through here. Every term is nicely set up for power rule. No parentheses, no denominator, variable, no radical. So everything is set up nice and ready for us to use. So y prime plus, what does x to the fourth become? For x cubed minus minus 16x. And then what happens to the last two terms? 10x becomes 10, good. And negative 12, 0. Okay, so every degree is dropping by 1, right? Okay, let's find the second derivative. Plus
12x squared.
Minus
12x.
18x, right?
Oh yeah, 18, sorry.
Okay, minus 16, and the 10 goes 0, right? Drops out. Okay. What pattern do you notice? Each time we find the derivative, what's happening? And the reason why is because degrees keeps falling by 1, right? Especially if they're whole numbers. If they're whole numbers, that means each degree is eventually going to start dropping out, right? Once they get that linear, then it goes to constant, then it goes to 0. So what's going to happen if we keep finding the derivative of every term? Yeah, eventually everything will zero out, right? That 4 will go to 3, will go to 2, to go to 1. So that's one of the nice nice features about these polynomials is that all the derivatives kind of go to 0. That's just one of the something to point out there. Okay, I'm going to finish this here. Every term, every derivative will have one less term, right, if we're dealing with a polynomial. Okay, notations. There's a lot of ways to represent the first derivative. So if something starts off as f, I can call it f prime to find the derivative. G of x, I can find the first derivative and call it g prime. If I start off with y, I can find the derivative and call it y prime. If I have y, I can also find the derivative and call it dy dx. So let me talk about what that means in more detail here. Dy dx means find the derivative of the dependent variable with respect to the independent variable So dy dx is very descriptive. It tells us that we're finding the derivative. It tells us what the dependent variable is, and it tells us what the independent variable is. Okay. So that's what that dy dx tells us. Right. Another way of writing this out, I didn't include it on this list here, is d over dx of f of x. That just means find the derivative of f of x. So you have all these different ways of saying find the first derivative. Okay, so likewise, you can imagine just following that pattern and getting to the second derivative. So if I start off with f, I can call it f prime for first, f double prime for second derivative. Y double prime of x can be a notation for second derivative, y double prime. And also this d2y over dx2, that looks kind of confusing. This doesn't mean take the first derivative and then square it, okay? So we're not doing any calculation with that 2. We're not treating that as an exponent. We're just treating that as a notation for second derivative. So whenever you see that d2y over dx2, that just means find the second derivative. Okay, we're not going to find the third derivative very often, but we can imagine the patterns continuing in the same process. F triple prime will be for a third derivative, y triple prime will be for third derivative, and then much like how this is written, d3y over dx2 would mean find the third derivative of y with respect to x. Okay, there's one note that I want to give before we do some practice problems. And it's power rule versus quotient rule. So I want to point out two problems here. Now, in the first scenario, if I wanted to find the derivative, I could go through quotient rule, right? The numerator is f, the denominator is g, f prime g minus f g prime all over g squared. That's fine. But my suggestion is if you only see a monomial in the denominator, there's only one term, and you don't see multiple terms separated by plus or minus, my suggestion is go ahead and split up into 4 separate fractions, or however many fractions you can split up into, clean up, and just rely on power rule. Feels a little bit cleaner. It's easier to get to where you want to go. It's not wrong if you go through quotient rule. It's just a messier process to clean up. Okay, so that's my suggestion. Go through product rule if you are only seeing one term in the denominator. And this is going to help us second semester as well when we're going the opposite direction. We're also going to rely on power rule for antiderivatives. And so that's kind of a good habit to kind of build, that if I only see one term in the denominator, I'm going to rely on power rule. It's not wrong for quotient rule, but it is just, it'll be good for us in the future if we're getting used to that process. Okay. And we'll practice with some of these problems on the back page. I did some of this with you when we did power rule introduction. Now, as soon as your denominator shows more than one term, then you're stuck with quotient rule. Okay, there's no other option except quotient rule, so you just have to do it with that one rule in mind. Okay, so power rule with one term, anything more than one term, you got to rely on quotient rule. Okay. So here are the steps that you would take for power rule. You would split into individual fractions. You would clean up each term, right? All the conditions, all the conditions such as, merging the terms, getting the variable to the numerator, no radicals. Then you can use power rule. For each term. Okay, so I don't want us to work this out just yet. We'll do it on the second page, but right now I just want us to make sure that you see that distinction, that yes, you could do quotient rule for every numerator and denominator function, but really want to push us to do power rule for that one instance and then rely on quotient rule for everything else. Okay, let's go to, actually, I think I want to save page 25 for tomorrow. So I want to go back and I wanted to do some more review practice with these power rule problems. I want to make sure, really getting that power rule process down, because it's so important for everything else that we're going to build after this. So if you can turn to page 13. And I want us to start with number 7 at the bottom. We may have seen some of this with homework, but we're just going to get that extra practice in. So page 13. All these are power rule problems. So look at your conditions here. Radicals converted to rationals. Denominator variables brought up. Parentheses resolved. All terms expanded. And then go ahead and try number 7. And then as a side note, sorry, how about this? As a side note to all parentheses resolved, let me add this additional note here. I say that all parentheses are resolved, but in other words, if you have any variables that are stuck together through multiplication, you got to get those cleaned up, merged together if I want to do power rule. Otherwise, I got to do product rule, and we don't want to, the rule of thumb is try to rely on power rule for everything. And if power rule doesn't apply because it's not fit or it's too complicated, then you explore your other rules. Then you explore your more complicated rule. But we never want to skip over the first rule that we want to use. Okay, so try number 7. So we got to get that x to be pushed together, right? It has to come up. We got to deal with the radicals there. Okay, so convert from radicals to rationals. Remember, when you are multiplying variables, you're adding exponents. You're adding exponents. Going the steps halfway through. Root x becomes x to the 1/2. 1 plus 1/2 is 3/2. So the variables are merged together, but it's still not quite in the right place. So we got to bring it up. Now we can do power rule, right? So power rule, bring the exponent down in front, multiply with any existing coefficient there, and then subtract 1 from the original exponent. And then after you find your derivative, clean up to present your answer. Any questions? All right, try number 8. Think about all the conditions that need to be applied or that needs to be met before power rule can be applied. About that, let's see. Get it cleaned up. I think the hardest part is just to get it cleaned up. I think the calculus portion is the most straightforward part, but getting to that point where you can hand the problem off to the calculus step, sometimes it's the most challenging. Okay, so that radical converts to a rational exponent. Make sure you distribute the 3x squared through, and then you can apply power rule. Once it's nice and clean, all the conditions met. Now you're ready to go through your calculus step. Whenever you're ready, back page, page 14. So number 9 and 10. Okay, so looking at number 9, I'll unfreeze this in a moment. But looking at number 9, how would you begin this problem? How would you begin your cleanup step? Yeah, FOIL out, right? Expand out. Make sure you don't just take that exponent and distribute that exponent through. You're going to miss something if you do that. Write the binomial twice, force yourself to FOIL, and then once you get that done, then you can worry about the x. All right, so it's easy to mess up this problem. So you want to make sure that you're taking the appropriate steps here. Okay, number 10. I see a numerator and denominator, but do I have to go through a quotient rule? No, right? There's only one term in the denominator. My preference is that you take the time to go through an easier process. Just clean up using splitting into individual fractions, resolve each denominator variable, and then go through to power rule. Yes.
And the answer to number 9, why is 75x cubed?
Oh, sorry, x squared. Right. So what you guys got? X squared. My bad. Got to subtract 1 from the exponent. Okay, so oh, sorry guys, I'm running out of time, right? Okay. Yeah, we'll pick this up tomorrow. You guys have homework for product and quotient rule. Don't get your phones. Sorry about that. Sleep.